Thank you very much. Thank you very much, and I would really want to thank the organizers for this invitation. It's the first time I'm here in this nice place, and I think the format of this workshop is really ideal. I will tell you, I will report actually on some recent studies we made on some proton radioactivities, and these studies, experimental studies, were done with the ACTAR TPC device that is shown here. Okay, I did not introduce myself. I apologize. So I'm Giovinazzo. I'm from the lab in Bordeaux in France. And in this presentation, there will be results from 2 experimental collaboration. And this is also thanks to the ACTAR TPC collaboration and the staff from Ganil and from the LIS separator. So I will first say a few words about proton emission. What happens when we go to the drip line? This will be very basic 4 words to introduce the topic. I will talk about this need for a new detector devices, which has already been introduced this morning. And I will present our device, which is ACTAR TPC. And then the point is here to show results of the results. So I will report on this two experiments. The one that was aiming at 2 proton radioactivity. Here it will be mainly qualitative points because these are really new results and the analysis is not done yet. And another one about the radioactivity, proton radioactivity from proton isomers. So just a few words about stability and proton emission. So okay, this is this well-known valley of stability, and with this asymmetry term that makes this parabola. Of course, I will not detail that. So, but because of this symmetry term, when we reach the sides of this map, we reach a region when the binding energy is not becomes negative, and the last nucleons, either protons, either neutrons, are not bound anymore by the nuclear forces. So the system becomes unbound, and so the idea is to go towards these drip lines. So when we are not very exotic, we have beta decay or beta gamma decay. This is the beginning of experimental studies. We can measure many things. Since it's not very exotic, we have high count rates can be achieved experimentally, so we can make precision measurements and so on. So here we are in a region when the Q value is not too large. The proton separation energy is typically in the order of 8 MeV. So all this is the states fed by beta decay are bound with respect to protons. If we go a bit further, if we go a bit further, this Q value increases, the proton separation energy decreases, and we can fit some states that will decay by proton emission. This kind of processes are important to study for different aspects, but it's also some processes interesting for nuclear astrophysics and measuring the proton and gamma competition. One point is that this proton probe is a quite precise measurement. It's an easy probe, and we can get some precise structure information on exotic stuff. So that's interesting on the experimental point of view. Then if we go even further, then it's open for several proton emissions. And then, so we start to have quite a complex decay scheme. If you see here, these are also nuclei that can be interesting for RP process, because these are the waiting points of the RP process. We can search for the direct emission. I mean, this was also some point discussed yesterday, raised by Olivier, to have non-ground state emissions, but in the case of beta decay, it has not been evidenced yet. But this kind of exotic decay is also the only access to the most exotic nuclei that you can produce on the proton-rich side of the value of stability. Because of this complex pattern here, there are many things that can be studied also. There are some statistical studies that can be performed because there is a high density of levels here. It's also, I did not mention it, but here, but sometimes it's also the first access to masses of very exotic nuclei, because you measure quite precisely the proton energies. Those ones are less exotic, so you already know their mass. So you can, with the isobaric multiplet mass equation, you can have the first information about the mass of very unstable stuff. And then finally, if you cross the drip line, then you reach a region where the nuclei are unbound with respect to 1 proton or 2 proton emission, depending if you are in an even or an odd mass. And of course, this was already introduced yesterday. And this is also where we are interested to go in one of the experiments I will tell you about. But there is, okay, so we want to go to the drip line. This is always something quite difficult, both on the experimental, on the theoretical side, and both on the experimental side. But there is also another way of going to those unbound systems is to use the energy direction. And here I show you 2 cases. These are high energy isomers. I will tell you about those 2 ones. So iron 45, which is bound, and nickel 54, sorry, and nickel 54 that is unbound. And we studied these ones for isospin symmetry studies near the n and z equal 28 shell closure. So this is to point out the context of these studies. So for a theory of this is complicated because you have many aspects that have been described in those days. Some effects like coupling to the continuum. You will see that in some of the work I will show. So the effects are dominated by extremely weak components of the wave functions. You have the problem of the dynamics of the emission. And in the case of the isomer decay, we will address the question of the isospin non-conserving terms in the nuclear interactions. And for experiments, of course, it's difficult because the more unstable you are, the more difficult it is to produce. You deal with short half-life, with multi-particle emissions, with very few events, or with a large background that you have to deal with. So there are many developments ongoing. So there are developments of facilities to increase the production rates and so on. And there is a need for new devices. This was also introduced this morning. And I will show you the time projection chamber type of device. And I will, in the following, during the talks, you will see that at some point that there is no other way for some of the measurements that using this kind of devices. So I will present our device, ACTAR TPC. So it stands for active target and time projection chamber. In the experiment I will show you, I will use it as a decay detector. So we will not use it as an active target as it was presented this morning. So this detector is born from 2 previous collaborations, the Maya detector that was mainly at Ganil. So they developed this TPC for nuclear reactions. And at Bordeaux, we developed another TPC that was used for decay experiments, which means ion stopping in the detector and decay measurement. There are other such type of devices that are developed or under development. I should mention this optical TPC from Warsaw, which was developed for the same physics program. You heard this morning about Texas A&M active target. And there is also I want also to mention ATTPC at NSCL because they use basically the same techniques as we use. So the principle, what we wanted with ACTAR is to have a full four-dimension measurement of the tracks, which means the trajectory, which is 3-dimension, but also the energy loss along the trajectory. So the idea is to have a full reconstruction of the ionization signal in 3-dimension. So we have a pixelized path plane. So the projections give you a 2-dimension information. The Z information is related to the drift time. This is a time projection principle. So, okay, this is a TPC principle measuring the Z coordinate with time. And then if we want 3D discretization of the chart, then we need to discretize the 3rd dimension. And this is why we developed the gate electronics, which will sample in time the signal while it's drifting towards the collection plane. And we go from a picture like that, where you have the ionization along the particle tracks, to some measurement. This is, of course, this is a schematic view with full voxelization of the charge. So the detector itself looks like it's basically a very simple device. It's a cube with gas in it. So there is the path plane that will collect the signal. And in order to collect the signal, you need an electric field as uniform as possible. So you need a drift cage. So here you don't see, but it's wires with potential difference, and a cathode which has a high voltage. This was developed at Ganil, and it's not an easy tool because you need to be as transparent as possible, but not sensitive to the box around is a ground, and you need to protect from that. So there is a real design on that. And then we had some developments to be done also on the pad plane, because we wanted a high density of pads. Our pitch it's 2 millimeters by 2 millimeters, but we have 16,000 pads, which is not an easy task to realize as a circuit to extract all those signals. So there were several solutions that have been developed. And and this electronics that is used for the digitization of all those channels, digitization in time for the time sampling. So this is the gate electronics that is used in the TPC at Texas, at NSCL, also at RIKEN. So this is called the generic electronics for TPCs, and it was developed between France and the NSCL. Okay, I will not go into more details on that. Just to sketch the timeline of the detector. I mean, the discussion were started in 2012, 2013, and the electronics started to be developed in 2014. We got the first boards where we could study the response of the signal and so on. This was actually important to extract the information from the detectors. Then there have been 2 demonstrators, one at Ganil and one at Bordeaux, that allowed for the characterization and the performance that we can expect from such a detector. And then the real detectors with the 16,000 channels have been started to be developed. So actually, there are 2 geometries for this detector, what we call reaction geometry and one that we call decay geometry. It's just one is a square and the other one is long. So we can cover a wider range with the same electronics and same principles and so on, but we just can cover a wider range of kinematics depending on the type of experiments. So the first test was done in 2017. This was in active target mode. This was part of the PhD thesis of Benoît Mauss. And then the experiment started in 2019. So I will present those 2 experiments that are in decay mode. Of course, in 2020, because of the COVID, everything was stopped. The second decay experiment was about to measure the 2-proton radioactivity of nickel-48. But there have been also some experiments in active target mode. And this year, a new running mode has been tested, which is called brochette, where we have two experiments in the same time. One first with the ACTAR TPC, and the beam goes through, and then there is a Coulomb excitation device behind for simultaneous measurement of the Coulomb excitation and inelastic scattering. I just want to the future. I mean, this is a kind of device that we plan to use at RIKEN for proton radioactivity. At TRIUMPH, there are some transfer reactions that are experiments that are accepted, and further it could be used also at GSI. But just to sketch, because I will not talk about these experiments, but since it's happening right now, I just wanted to show you how it looks like. So this cube is the active target. We can put silicon detectors around and to measure the scattered particle. And just to show this transfer reaction experiment that took place in March or April. And these are, of course, very preliminary results, but just to show some particle identification, we can perform the kinematic lines for the DD prime channel. And the idea is to build some excitation energies from that. It's a different channel, but all this work is done by a PhD student from Santiago. And then this brochette mode, it looks like that. So you have the beam coming here. The detector is there, and then the 0-degree detection is here for the Coulomb excitation. So you have gamma detectors, and you have the record identification, and these are also the kind of measurement. This is, I mean, the experiment took place just right now. So you see here is a kinematic line. We see here we mainly see the elastic, and this is the kind of reconstructed energy. Very, very preliminary. This is in the case of argon 46, which was a test. So just to show you in this experiment how an event can look like. So here you have, this is the XY projection of the signal in the detector. You have the beam coming here, and the scattered proton is here. And also what you see here are delta electrons. So you have to deal with that. And because I mean the detector is it can be transparent to electrons, but if you need some amplification, you see them, and it's a very nice picture, but it makes the analysis a bit more complicated. You have also here you can see pilot, because you need a lot of beam for few reaction events, and this is also why we have also this attenuation along the beam line, to reduce the high signal from the end. Okay, this is all I will say about this campaign. I will first talk about this two proton radioactivity experiment, and I added also that we had also several beta multi-proton decays in this experiment. Just okay, the context of this measurement is the following. So this decay mode was predicted in the 60s. The first calculation were done by Galitsky, and it was observed for the first time 20 years ago by two collaborations, one at GANI, one at GSI. But this was an indirect observation. So the nucleus was implanted in a silicon detector, in a solid state detector, and you measure only the energy of the emitted proton and the half-life. So only global quantities of the decay. There have been other experiments of the same kind, and so nickel zinc 54 and nickel 48 have been established as emitter, and the last one that has been observed is krypton 67. I'm talking about ground state, long-lived ground state to proton radioactivity. I will come later on this one because it was important. So at the beginning, we had only very few information for comparison with theory, basically half-life and the Q value, and actually to compare with several formalism. But actually, even Q value was a parameter of the calculation. So basically, we were comparing only half-lives, and there was no dynamics in the comparison. Then there was a three-body model that was developed, but actually I can come to this. This three-body model that was developed by Grigorenko and Zhukov. And this was this of the three-body Schrödinger equation. And the interesting feature for us is that they were predicting some energy and angular correlation patterns that were mentioned yesterday by Vitek. And what was claimed is that the pattern we may observe should be sensitive to the structure of the emitting nucleus, as you can see here, as in the case of iron 45, depending on the occupation of the wave functions. So this was one of the points discussed. Of course, it's worth measuring that if we can learn something from those correlations. This was part of the discussion yesterday. What do we really learn about from that? But to measure this kind of correlation, we need those tracking experiments, so those new detectors. So I mentioned that there were previous detectors for that, the one in Bordeaux and the one in Warsaw, and that they allowed for the first direct observation of this two proton emission with few counts in the case of iron and zinc at first, but then with the best result, the most significant result is a measurement from the Warsaw colleague at NSCL, where they had 75 counts of 2p events, and from this they could build this angular distribution. And this basically sums the results at that time. So this was basically 10 years ago. And comparing to this three-body model, it was quite okay in the case of iron 45, because if the best agreement is obtained for a small component of the p waves, which is expected for iron. Not so good in the case of zinc 54, because here we would expect a higher occupation of those orbitals, but this was done with extremely limited statistics. In the case of nickel 48, we have a doubly magic nucleus, so this should be a pure configuration, and I will show later what would be expected with such a model. But then, oops. So what has been developed by us as experimentalists with Axel Brown is a kind of story model or whatever, where we took the dynamics from the three-body model, but this model has no structure inside. I mean, the structure is put artificially ad hoc, and the emission amplitudes were calculated from shell model configurations, and putting them together to try to extract a more realistic half-life. And this is what Alex Brown called shell model corrected half-lives. And it was working quite okay for those three cases. But when we measured the Krypton 67 at weekend, then it was not working at all anymore. We were factor 20 off.
But there you use the predictions of Brown or because it doesn't have prediction for...
No, for Krypton there was no prediction.
Okay.
But I mean, to search for candidates, basically the first candidates were proposed even in the 60s from a very simple tunneling calculation, which can be one order of magnitude away or even more. But actually, what's his name? Well, in the 60s, they already predicted the most favorable region to be the mass 50. Goldansky, thank you.
For the Krypton, they use the GXL model space?
No, it was not calculated. But for us as experimentalists, we look at the drip line. You search something where the Q2P is positive and the Q1P is negative. And then it should give two proton radioactivity.
We were confused because you were saying at the beginning that you had some calculation from Alex Brown, then you moved to Krypton 67, and there you don't have calculations from.
Yeah, but, okay.
I know that.
Yeah. But at this stage, you mean?
No, at this stage,
Is a factor 20 if you want to
Ah.
know.
yeah, so
Yeah.
it's not, you have a factor that is very different, but you didn't use a proper shell model.
Yes. In that case, yes. But I cannot tell you. Okay. Sorry, I misunderstood. I misunderstood. No, okay. I cannot tell you what was exactly inside the shell model calculation. I mean, we can go through the papers, but no,
It'd be good to make a
but anyway, you will see some other calculations after, because this triggered other calculations, and you can already guess here. But
yeah.
So
no, this,
Yeah, but I mean,
so this was the point in 2016.
there would be a decent shell model calculation.
There is
we get the same result. I mean, it should be interesting.
But anyway,
this system is well defined and is proton and bound. What are the decent shell model calculations? Are you talking about?
But they cannot produce the zero control material.
They cannot do it for the unbound system.
Well, but unbound, I don't think it's not very super well unbound. Okay, I don't know. I just say
it's unbound by 1.5 ME.
1.5, and you have a huge Coulomb barrier.
So there have been two hypotheses for this discrepancy or this mismatch. So the first one was proposed by Leonid Grigorenko, saying, okay, but this may depend on the exact position of this intermediate state, because the mass measurements are extrapolated, and then depending on this on the position of this state here, you can go from two proton radioactivity to sequential decay. But if this is true, then you have this sequential decay that opens. But then, so he made some calculations. So this is the experimental energy here, and the experimental half-life, and playing with this resonance energy. He could get close to the experimental value. If this is the case, then we will see it not in the energy in the angular correlation, but in the energy correlation, because here you will have favored specific proton energies, and you should see some shoulders in this distribution. But then there was also another calculation. Okay, as Vitek just mentioned, Krypton is in a region of large deformation, and so they made this calculation in the Gamow shell model couplet to continuum. And so I will not tell you about the details of that, but basically going to a deformation of 0.3, then the half-life was coming really in agreement with the experiment. And another interesting feature of that, and it was mentioned also yesterday, is to measure the correlations as the angular and energy correlation. And they calculated for Krypton 67, but also for nickel 48, which is spherical and which was used as a benchmark of the model. And you will stop me if I say something wrong. So our idea is to measure both of them and to test this model, because in this model, we have in a consistent way the structure and the dynamics of at least more than in the previous model. So the idea is to measure both angular distribution. And I mean, we can compare the two hypotheses. So in the case of the 3 model, we don't have a prediction for nickel 48, but comparing what we have for iron and for zinc, we expect something here for a pure configuration and nothing here. And in the in the case of Krypton, so you see that the pattern is not exactly the same. Huh? So the idea for us is to compare experimental data with the models. And in the case of Krypton, in one case we have the angular distribution, and in the other case we should see it in the energy correlations. So
you said that in nickel 48 you don't expect
yeah, but this is in the model of the three-body model.
Yeah, is there an easy way? Okay, maybe we can discuss later. I will ask the question.
Okay. So in principle, this could be done at Ganil, and this could be done at Riken with ACTAR. And this is why we went to Ganil to make this experiment. It was last year. Here is just an identification plot, a partial one, but actually the result is that we did not get the statistics we expected. It's already 10 minutes. No, I have to be faster. So we got only, I mean, stopped in the device. We got only 7 events, so we will not do much with that. In addition, only 2 of them because there is always competition with beta decay. So we've seen several beta decays, only 2 proton decays. This is preliminary. Maybe there are still some missing data, and we missed some of them because of the dead time, or if the proton is emitted on the side of the detector, we miss part of the emission. This is an example of the implantation, then the decay, and also the decay of the daughter, because the daughter is beta proton emitter. I'm sorry, it's only 1p here. We get a bunch of other information in this experiment. Many beta delayed proton, 2 proton, 3 proton decays. This is a kind of selection that my student did of events. We have few events of 2 proton radioactivity from iron 45. And what is also interesting and illustrates the need of active targets is the low energy. This is a proton, emitted proton. It's a low energy protons. And this is interesting in the case of astrophysical interest to study the proton gamma resonances in inverse kinematics. And this was illustrated by this plot that actually probably comes from Texas because it's a plot from Lolly. This was shown everywhere. The problem with silicon detectors, you are killed by a huge beta background at very low energy. And in astrophysics, you are interested in low energy protons. So you are killed by beta background, while with a gas detector, you can get rid of the betas. And just to show you an example here in our experiment, we got, for example, the manganese 46 decay, which is interesting. I should have mentioned it, but there is a proposal from Andre Miguel Sanchez on astrophysical interest on that. And here I show you, this is a very preliminary result. Here we have the track lengths of the protons emitted by manganese 46, and we go to relatively low lengths, which corresponds, this is a correspondence between the track lengths and the energy. So we go below 200 keV. This needs to be precise because the resolution for now is not optimal. But this is of interest for the type 2 supernovae studies. And come on. So this is an ongoing analysis. I will go quickly because I want to go to the next point. We will not have the statistics for the 2 proton radioactivity. There will be another. There is an experiment that will be proposed by the Varso colleague at FRIB. I hope they will be more successful than us. This is just to show you the kind of. This is a Bragg peak of the 2 protons, just to show you. But all this analysis is ongoing. There are some quite complicated tools to develop. This is now done by my student. Future, this I will skip also, but just to answer your point, which was not your point actually. We look at all those even Z nuclei are potentially candidates. So it will be interesting to go along that, and this will depend, of course, of the availability and the intensity. So the idea is first to search for candidates with standard experiment, and if you find a good candidate, go for a tracking experiment that is more ahead. Sorry, I'm a bit too long. Now I wanted to show this result because it's a very nice measurement that we did. on this isospin symmetry of nickel and iron 54. So basically, the idea, if we compare those two nuclei close to the n equal 28 shell closure, we can compare the BE2 and BE4 of this 10 plus isomers, which is kind of unique case like that. The point, okay, iron is stable. This was well known from gamma spectroscopy, and nickel is unstable, and the proton separation energy is there, so this state is unbound with proton emission. So it has okay, both have a very short half-life, and such nucleus is accessible only at fragmentation facility. And it was partially known from the rising campaign collaboration that measured only gammas at GSI. So they had the gamma decay, but they also had this gamma, and from this they deduced this transition. There was this missing transition, and if you want to compare the mirror nuclei, you need the exact partial half-lives, so you need the full decay scheme. And it's proton decay with very high angular momentum. There is also a possible two-proton branch, but this will be neglected completely because the expected branching ratio is something like 10 to the minus 6. And we cannot measure simultaneously this and this. But so this is a quite complicated case because with high angular momentum, it's complicated on the theoretical point of view. For experiment, it's complicated to produce this exotic stuff. There was an attempt by fusion evaporation, but it was not successful. We did it like at GSI, standard fragmentation experiment. We produce, you see it, this is, nickel is easily produced because it's not very exotic, but to get it in the isomeric state, it's more difficult, and we have got only something like 0.1 to 0.2% of these ions produced in the isomeric state. Playing with the momentum acceptance of the separator, we can increase it a little bit. This is what we did. But now, what is the experimental difficulty is that you stop your ion from fragmentation, you stop it in a detector volume. And in the same detector volume, you will have almost simultaneously the 1 GeV signal from the ion and the small signal from the proton. So you cannot do that with standard silicon detectors, and this is where you need a time projection chamber. Come on. And because here you have the huge signal from the ion, and if the proton goes in another direction than the beam, then you can separate it. And this is actually this was the first campaign of the detector physics campaign of the detector in 2019. So how we extract the experimental information? So you have the beam coming here and the proton that is emitted. Okay, I skip all the analysis. I will show you just the results. Okay, what we measure is we measure the track length and the lifetime, because when the signal is drifting, since the proton is emitted after some delay due to the half-life, there is a shift in time between the ion track and the proton emission. And here we measure the track length, which is basically the energy, and the time difference between the end of the ion track and the beginning of the proton track, which gives us the half-life. So
it was wrong there, the experiment.
Yeah. So now we get the full experimental measurement, but to get the effective branching ratio, we need to get an information about the detection efficiency, because intrinsically the detector is 100% efficient, but you have proton escaping the volume or going along the track, whatever. And this is different depending on the length of the track. You see, one of the track is something like 35 millimeter, and the other one is 20 millimeters. So the probability to escape is not the same. So for this, we just developed a full simulation, and I will go very quickly. So I skip but then we get to the final numbers, which are the effective branching ratio of the gamma decay and the proton decays. So mixing our results with Proton and the results from the rising company. So to compare with theory, first we can calculate the half-life. This was calculated by Alex Brown, and taking into account high angular momentum orbitals that are given here, because I mean the proton half-life is completely governed by those by high L angular momentum. But these are components of the wave function down to the 10 to the minus 6 of the wave functions. This gives a quite good agreement for the L equal 5 transition to the ground state, but not so satisfying to the other one. So Alex was pointing out that there could be a mixing with another 10 plus state, because this mixing would not change that much the half-life for this transition, but it would change for this one. Or maybe the space was too truncated. So it works not so good. But then we have also now all the elements for the mirror comparison. This is what was missing for the comparison to compare for this isospin symmetry comparison. So Dirk Rudolph made this work. So here are the different terms taken into account for non-conserving interaction terms. And here they are mixed together, different choices of the interaction terms. And as a result, we can get a good agreement with the experimental points in black. Here, the theoretical curves are a combination of those ones. And this is with a different type of interactions, but you see that it doesn't change. So we could think that there is a good agreement with experimental results, but actually there is a problem, because I mean, for the parametrization of these terms that were reproducing this, there is some. This requires different parametrization in this case and other known cases in the region. And we could also calculate from the experimental data the effective charges. And here also we can get to results, but it's not in agreement with what is expected in the region. So what we did, just to conclude, we did this new tracking experiment with 3D tracks and decay time. We got this complete decay pattern. There is another isomer decay was done in the same experiment with even higher angular momentum. Actually, this is the first proton radioactivity that was ever measured in the 70s. Here, just to show the plot, this is an analysis that was done by Thomas Roger for the ACTAR side. But the theoretical interpretation is not yet completely satisfying, but this opens, these are completely new studies, comparison between experiments and theory. There are a few other measurements that are foreseen with here. Sorry for being too long. I just want to thank the different collaborations. The Nickel 54 collaboration led by Dirk, the ACTAR and LIS collaboration, and the PhD students that provided a lot of material in that. Thank you very much.